Now I'll be explaining solar cell characteristics and different parameters of solar cell. Now coming to the solar cell characteristics, basically there are two characteristics, one current voltage characteristics and power voltage characteristics. We call it as IV characteristics and PV characteristics. Therefore, coming to that first one, current voltage characteristics. For current voltage characteristics means IV characteristics. Here for a solar panel, here this is the IV characteristics of a solar panel, and we have see that one corresponding to the out voltage 0, the corresponding current we call it as short circuit current. This is called the short circuit current, and here this is called the open circuit voltage that corresponds to zero current. So this is corresponding to zero voltage, that's called short circuit current, and this corresponds to zero current, that's called open circuit voltage. Therefore, this is the IV characteristics of a solar cell. Now, to calculate or to get the PV characteristics, power voltage characteristics, as you know that one, power is given by the product of voltage and current. Now we take, for example, in order to corresponding to this point, current equal to short circuit current and corresponding voltage is equal to 0 here. Therefore, the product will become 0. Therefore, that starts from here. Now, as this proceeds here, as the voltage increases, you can see that one, the current is a constant current, short circuit current. We'll take the product of this current and the corresponding voltage. Then the power will be linearly increasing. The power will be linearly increasing. That is the power axis, this one. The power linearly increases, and as you see that one, the power will be reaching to a maximum power, that's called maximum power point. That is called, this is called corresponding to the maximum power point. And then again, as you know that one, this IV characteristic, it is dropping here. Therefore, the product will begin dropping, or the PV curve that will be dropping down, and that reaches to this point. Therefore, this is called the PV characteristics corresponding to this IV characteristics. Therefore, this is called the maximum power point, or this is the maximum power. The power corresponding to the maximum, the point corresponding to the maximum power, and the corresponding voltage we call it as VMP, and the corresponding current we call it as IMP. Therefore, the IMP into VMP, that is the maximum power Pmax. That is the Pmax. Therefore, this is the IV characteristics, and this is the PV characteristics of a solar panel. For certain irradiation, or as the irradiation changes, or as you know that is radiation or insolation, as insolation changes, for example, say here, this is the IV characteristic corresponding to a insolation of 1000 watts per meter square. 1000 watts per meter square radiation. The current voltage characteristic of a solar panel is this one. Therefore, this current corresponding to the short circuit current for the radiation of 1000 watts per meter square. Now, as this irradiation changes, for example, it is changing from 6000 watts per meter square to 600 watts per meter square. As the insulation changes, what is happening? The short circuit current reduces. Therefore, short circuit current reduces, and again, it is meaning that this IV characteristic will be coming down to this one. Therefore, this is corresponding to current voltage characteristic of a solar panel corresponding to 600 watts per meter square insulation. Again, if you reduce the insulation to another value, say 400 watts per meter square, then that going again down. Therefore, this is the IV characteristics of solar cell corresponding to different insulation, starting from 1000 watts per meter square, 600 watts per meter square, 400 watts per meter square. Continuing the effect of insulation on PV characteristics, already as I explained in the previous slide, as the insulation changes, the IV characteristics is going down. In this case, this is 1000 watts per meter square, and here this is 600 watts per meter square. This is corresponding to 400 watts per meter square. Or basically, the short circuit current gets reduced as the insulation changes or reduces. The short circuit current changes. That change in short circuit current is more than the change in open circuit voltage. For open circuit voltage also slightly changing, but short circuit current is changing more. For corresponding to this one, the PV characteristic, as you see that one, the PV characteristic also that will be going down here. This is corresponding to 1000 watts per meter square power voltage characteristics. And again, as this corresponding to this 600 watts per meter square, the PV characteristics going down. Again, this is called the PV characteristics for the 400 watts per meter square insulation. So this is corresponding to this is the maximum power corresponding to 1000 watts per meter square insulation. This is the maximum power corresponding to 600 watts per meter square insulation. And this is the maximum power corresponding to 400 watts per meter square insulation. Therefore, as insulation reduces, you can see that maximum power output is getting reduced. Now let us see the different solar cell parameters. That is, coming to the first one is the open circuit voltage, VOC. It's called open circuit voltage. Open circuit voltage, this is the maximum voltage that the array provides when the terminals are not connected to any load, or when terminals are open circuited. When PV terminals are open circuited, what is the maximum voltage? That is what we call it as open circuit voltage. This value will be higher than the maximum power, that is maximum power point. That is, this is the corresponding VMP, and this is called open circuit voltage. For open circuit voltage, magnitude will be more than the voltage corresponding to the maximum power, or which relates to this value is higher than VMP, which relates to the operation of the PV array. And this value depends upon the number of PV panels connected together in series, because rather than a single cell, we'll be connecting the cells in series. Therefore, this value of this open circuit voltage depends on the number of cells that are connected in series. Therefore, as we already seen that one, this is the IV characteristics of a solar cell, and this is the PV characteristics of a solar cell. Therefore, here first one is the open circuit voltage, means that corresponding to zero current. Therefore, zero current means this axis, this is the open circuit voltage corresponding to different insulations. So this is the open circuit voltage, and of course we will see that what is the short circuit current, and this is the power, or this is the maximum power, and the voltage corresponding to the maximum power called VMP, and the voltage corresponding to the the current corresponding to the maximum power, we call it as IMP. Now let us see the second parameter of the solar panel, that's called short circuit current, that's represented by ISC. Short circuit current is the maximum current that provided by a PV array when output are connected or short circuited. When output is short circuited, that when voltage is made zero at the output side, what is the maximum current that it can supply? That's called the short circuit current. Short circuit current, and this value is much higher than the maximum power corresponding to maximum, or current corresponding to the maximum power, which relates to the normal operating circuit. Therefore, the current corresponding to the maximum power is called this one, IMP. And this short circuit current means when this is shorted, what is the maximum current that it can supply? That's called short circuit current. Therefore, this is the short circuit current, and this is the current corresponding to the maximum power output. In the previous slides, we have seen what is the open circuit voltage and what is the short circuit current of a solar cell. And now we see that what is the maximum power point. As we have already seen that this is the PV curve of a solar cell, and the maximum power, that is this point, that is called the maximum power point, or maximum power P max it is called. Before the load is connected, the module, as the module facing the sunlight, will produce an open circuit voltage VOC, because it is open circuited. This is open circuit voltage, this is not connected, current equal to zero, a voltage that is produced, that one, that's called the open circuit voltage, but no current will flow. If the terminals of the modules are short circuited, which does not, under short circuit condition, then the voltage will be zero, there will be maximum current, or the current corresponding to that is called short circuit current will flow. But output voltage in both cases, since here the current is zero, voltage output power equal to zero. Here voltage equals zero, again power output equal to zero. In both cases, that is in this case as well as in this case, the power output equal to zero. But the output voltage will, in both cases, since the power is the product of current and voltage, no power is delivered by the module. Now let us see when a load is being connected, what happens that one. Then we'll be seeing that the current and voltage will be linearly increasing, and that reaches to a maximum power, that's called P max, then again that reduces and reaches to 0 power. So this is the PV curve, and the power corresponding to this one we call it as maximum power, and the voltage corresponding to that called VMP, and this is called IMP. Continuing the maximum power point, as we have already seen that this is the IV characteristics of a solar panel, or again this is an IV characteristics, and this is the PV characteristics or product of voltage and current that is linearly increasing, reaches to maximum and reduces to 0. And this power we call it as maximum power, and the voltage corresponding to that is called VMP, and the current corresponding to that is called IMP. The product of IMP and VMP will be maximum power output. Now let us see, as the load changes, actually as the load changes here, as you know that the output of the solar cell is connected or across a load, I mean through a load, the current flows that one, and the load depending upon the load resistance, as you see that one, this is the PV characteristics of the solar panel. Now when a load is being connected, what is the current through the load and the voltage across the load, that is related by, for example, if it's a resistive load like that one, the current and voltage are linearly related. Therefore, this is the case where it has got a resistance that is that IV characteristics of the load is like this one. Okay, now the operating point is at what voltage or current that operates, that depends upon the point of intersection of this load characteristics as well as panel characteristics or solar panel characteristics. Therefore, that will be operating at this point, meaning that that will be operating with a corresponding current as well as corresponding voltage. Now, as the load changes, for example, you are changing the load and such that the load line, as the load line means IV characteristics of that load line passes through the maximum power point. That is, this is the maximum power point of, this is the maximum power, and that's corresponding point. Through this one, if the load is passing through that one, if the load resistance is adjusted in such a manner that it passes through this maximum, this one, then that will be operating with the corresponding, in this case, corresponding voltage VMP and corresponding current. Therefore, here this is corresponding to the maximum power. Therefore, in order to get to make it operate in maximum power, what we have to do is that the load resistance we have to adjust. We have to bring the load resistance or the characteristics of the load that is to be brought to pass through the maximum power point. In that case, you will be getting you can extract maximum power from the solar. When the load is connected, as you these are when the load is connected, some combination of the current and voltage will be result, and that will be making a power here. To figure out how much power is delivered, we have to consider the IV current. How much power is being delivered? In order to calculate that one, we have to find out what is the IV characteristics of the load as well as the characteristics of the solar panel. Therefore, in this case, this is the operating point. But if you change the load resistance in this way, here this is operating point. Therefore, the corresponding voltage is this one and corresponding current is this one. Therefore, you can adjust the resistance of the load so as to pass through the maximum power point. So I mean through this like this one, so that you will be getting a maximum power output. I am continuing the maximum power point and concept here, as the figure shows the IV characteristics as well as PV characteristics of the, of course, photovoltaic module, identifying the key parameters like we have already seen. What is the open circuit voltage, what is the short circuit current, this is the open circuit voltage and this is the called short circuit current, and the power is the product of voltage and current. As you saw, I already explained, the power is the product of voltage and the voltage as well as the current. That product is the power, and the power delivered by the module at the two ends of the IV characteristics. At two ends here the power will be 0, because here voltage equals 0 and here current equals 0. Therefore, power will be 0 at these two ends of the PV characteristics. The output power is 0 since either current or voltage is 0 at these points. And the maximum power point is the spot near the knee of the IV curve, at which the product of the current and voltage reaches its maximum. The product of the current and voltage reaches to a maximum, that we call it as maximum power point, or it is called that corresponding maximum Pmax. And the voltage and current at this maximum power points are designated as VMP and IMP. I'll already explain here. This voltage is representing as maximum power point VMP voltage, and this one called, it is equal to current corresponding to maximum power point IMP and VMP, and the product of that we call Pmax. Now I'll be explaining what is meant by standard testing condition, STC. Now we have seen what is PV and IV curves of the solar module that shifts around as the amount of insolation changes and as temperature changes. Because this IV and PV characteristics will be shifting as the insolation level or that changes, as well as that also a function of the temperature. Temperature of the cell also as changes that will be changing. We see, they will be seeing later that one. Therefore, the standard testing condition STC have been established to enable the fair comparison of one module to another. Just to compare one module with another module, there is a condition is to be made. That's called standard testing condition. And the standard testing condition means the irradiance or insolation that will become 1 kilowatt per meter or 1000 watts per meter square. The radiation is equal to 1000 watts per meter square, that we call again one sun, we call it as, with the spectral distribution of air mass ratio. We'll see that one, air mass ratio equal to 1.5, and of course the temperature equal to 25 degrees centigrade. The temperature will be 25 degrees centigrade, and the solar radiation will be 1 kilowatt or 1000 watts per meter square, and the air mass ratio equal to 1.5. Air mass ratio equal to 1.5 means that here, say, solar radiation is coming like this one, falling on this junction here, and if this angle equal to beta, the air mass ratio is related to this angle by this equation. Air mass ratio equal to 1 by sine beta. 1 by sine beta is equal to air mass ratio. Or if you see, for example, air mass ratio equal to 1.5, if you calculate beta, that will become 42 degrees. However, if the solar radiation is falling with this beta equal to 42 degree angle, and if there is 1000 watts per meter square is the irradiation at 25 degrees centigrade, under this condition we call it as standard testing condition. For different irradiation, as you see that one, the solar the IV characteristic shifting like this one. Manufacturers always provide the performance data under these operating conditions, under standard testing condition. Now let us see the effect of temperature and insolation on IV characteristics. Already I have explained the effect of insolation on IV characteristics, because as insolation reduces, the IV characteristics or the current voltage characteristics shift towards, or short circuit current reduces. Therefore, this is the IV characteristics corresponding to variation in insolation. And in this case, we have kept the temperature as 25 degree centigrade under standard testing condition. Now let us see that one. Again, this air mass ratio that also already seen, that beta value kept at that value, that is 42 degree. And in that case, air mass ratio is kept at 1.5. And here the irradiation is kept at 1000 watts per meter square. And we are changing the temperature. The panel temperature is changing. Again, as you see that one, as temperature is increasing, what happens here? The open circuit voltage reduces. Therefore, this curve is shifting towards left side. Here, as the temperature, solar panel temperature increases. This is the change. As temperature increases, that curve or the IV characteristics will be shifting towards left side. In this case, we are keeping the irradiation as 1000 watts per meter square, but temperature is changing. Therefore, the irradiation as the IV characteristic is shifting towards left side. Therefore, IV curve shift with a change in cell temperature as well as insolation. The current voltage characteristics curve under the various cell temperature and irradiation levels for a typical PV module, as cell temperature increases, the open circuit voltage, can say that one, as the temperature increases here, can say that VOC decreases, open circuit voltage reduces. VOC decreases substantially, that reduces as temperature increases, but short circuit current is not much reducing. Therefore, here ISC is not, increases only slightly. ISC increases slightly, thus effectively decreasing the maximum power and efficiency. Therefore, as solar panel temperature is increasing, the effect is that open circuit voltage reduces, or we can say that curve is shifting towards left side, or can see that the product of that one gets reduced, or output power, the power output available is getting reduced as temperature of the solar panel increases. And here, as irradiation increases, the power output is increasing. As we have already seen that maximum power point, this relates to the point where the power supplied by the cell that is connected to the load is the maximum value, where maximum power point is the product that the IMP and VMP, that product equal to P max, that is the maximum power output, and that will be in watts and or P watts, that is WP, that will be indicated as WP uh, in the specification sheet. It will be represented as WP. That is the product of this VMP and IMP. Okay, now let us see another parameter, but we call it as solar cell efficiency. Solar cell efficiency is defined as the ratio of the maximum electrical power output to the radiation power input to the cell, and it is expressed as a percentage. And it is considered that radiation powers on the earth is about 1000 watts per meter. We will be calculating this efficiency under standard testing condition, that is 1000 watts per meter square, and of course the temperature is 25 degree centigrade, air mass ratio equal to 1.5. Therefore, if the exposed surface area of the cell is a meter square, solar panel area equal to a meter square, then the total radiation power on the cell will become 1000 watts per meter square under STC. And if the area equal to A, panel area equal to A meter square, therefore 1000 into A, that much watts is the solar power input, that one, or sun power input, that one. Hence, the efficiency of the solar cell may be expressed as, that is, what is the maximum power output, that is the electrical power output, divided by what is the radiation maximum solar input, PM. That ratio we call it as efficiency of the solar cell. Therefore, it is equal to PM divided by, since we are considering a standard testing condition for 1000 watts per meter square, therefore PM divided by 1000 into the area of the panel in meter square. Therefore, 1000 into A. For P max divided by 1000 into A is the percentage of efficiency. Continuing the solar cell efficiency, the efficiency of solar or photovoltaic array is a ratio between the maximum electrical power output that array can produce compared to the amount of solar radiation hitting the area. Normally, the efficiency of that percent, the typical solar cell or the solar array efficiency is normally around 10 to 12%, or depending upon the type of the cell, monocrystalline or polycrystalline or amorphous or a thin film, depending upon the efficiency will be changing that one, but maximum efficiency is not less than 20% only at present here, solar cell efficiency. Continuing the solar cell efficiency, in order to calculate the maximum efficiency of a solar panel, we need to divide the panel power to sun power. What is the panel power divided by the sun power? That is expressed in percentage into 100. Therefore, to calculate the sun power or the solar irradiation power like that one, it is equal to, under standard testing condition, 1000 watts per meter square. Therefore, 1000 watts per meter square into the area of the panel in meter square, that is the sun power that is falling or that is hitting the solar panel. Therefore, that is the input as such. And output is the electrical power output. Therefore, efficiency is always output divided by input. Therefore, the solar panel power output, that divided by this sun power expressed in a percentage into 100, that is the efficiency of the solar panel. Therefore, that is equal to solar panel power divided by, as we already seen, it is equal to 1000 watts per meter square into the area of the panel in meter square into 100. Therefore, this is the percentage of efficiency of solar panel. As an example of solar cell efficiency calculation, we are taking a 300 watts rigid frame panel with a monocrystalline silicon cell, and its power is equal to 300 watts, or let's we call it as it is equal to 300 watts or 0.3 kilowatt, and the dimension is that 1.64 meters long and 0.9 meters wide. Therefore, this is a solar panel size, and the power output equal to 300 watts. And what is the efficiency? That's a question. Efficiency. Therefore, now to calculate the efficiency of photovoltaic electrical power output, that is nothing but 300 watts. That divided by solar input power into 100. Now we have to calculate what is the solar input power corresponding to this panel dimension. Therefore, here electrical power output equal to 300 watts or 0.3 kilowatt, and solar input power for an area of 1.64 into 0.99 meter, that is 1.64 meter into 0.99 meter, that's the area of that one, which is equal to 1.623 meter square, Under standard condition, you know that 1000 watts per meter square. Therefore, here 1000 watts or 1 kilowatt per meter square into this area, whatever you are calculating, 1.6236 meter square. That is multiplying that one, we'll be getting it is equal to 1.6236 kilowatt. Therefore, this is the sun power input or solar input power, and this is the electrical output power. For 300 watts is the electrical output power, and here 1623.6 watts is the solar input power. Therefore, the efficiency is given by output power, that is 0.3 kW divided by 1.6236 kW into 100, or we'll be getting 18.4 percentage. Therefore, the efficiency will be 18.4 percentage of that. Solar cell efficiency is only for 18.47 percentage. Therefore, we take the standard testing. Normally, when we are calculating this one, we'll be taking the standard testing condition, that is 1000 watts per meter square and temperature equal to 25 degrees centigrade. One more parameter is the solar cell parameter, or that's called fill factor. Fill factor FF. Fill factor is another quantity that is often used to characterize module performance. The module performance can be characterized by this fill factor. And the fill factor is the ratio of the maximum power Pmax. Therefore, this in this case maximum power Pmax that the solar cell can actually provide under normal operating condition to the product of open circuit voltage times the short circuit current. For this Pmax divided by the product VOC, that is the voltage corresponding to that, but so not VOC, the not the voltage. What is the maximum open circuit voltage VOC, and what is the short circuit current, that product. Therefore, Pmax divided by VOC into IOC, that is VOC open circuit voltage into the short circuit current. Therefore, this fill factor that gives an idea of the quality of the array, that, and the closer the fill factor to 1 unity, the more power the cell can provide. Therefore, if it is near to 1, it is good. Therefore, the fill factor is the ratio of the maximum power output divided to the product of open circuit voltage and the short circuit current. For fill factor equal to Pmax divided by VOC into ISC, or Pmax is given by, of course, Pmax, or we can calculate Pmax from this equation. Pmax, maximum power output, is given by fill factor into VOC into IOC. For the fill factor increases, the maximum power output will be more. So for this is a relation, this is a relation giving the, give an idea about what is the maximum power output for a given fill factor. For Pmax equal to VOC into ISC into the fill factor. An example here, open circuit voltage equal to 30 volt and short circuit current equal to 10 amperes. And maximum power, that is this maximum voltage corresponding to the maximum power is given by 25, and the currents corresponding to the maximum power that's given by 3 ampere. Therefore, the product of this one and this one, that 25 into 3, that will be the maximum power output Pmax, and the product of VOC and IOC, that is taken and that's given, that is substituted in the denominator. Therefore, this ratio, that is 25 into 8 divided by 30 into 10, or that will be giving 200 divided by 300, or 0.67. Therefore, the fill factor in this case equal to 0.67. Therefore, if fill factor is near to 1, that will give that gives an idea, that gives more power of the cell that can provide. Therefore, that is the fill factor, another parameter of the solar cell. Therefore, we have seen what are the parameters: open circuit voltage, short circuit current, then maximum power point Pmax, then what is the voltage corresponding to maximum power VMP and IMP, and the percentage of efficiency, and of course the last one, fill factor.